Hello, students. Today's topic is one that I would very much prefer to be covering in the classroom with the use of our CAD software, because it makes a lot more sense to me to talk about CAD modeling when we can actually do some CAD modeling. But working with what we have, I want to make sure before we finish up the year that you have at least a little bit of exposure and experience with parametric modeling. It's a more advanced CAD modeling technique that is a very useful one, and especially if you're going to go on and take more classes in technology like SIM next year. Parametric modeling is something you want to have at least a little bit of familiarity with. So let's get into it. Brief overview of what we're going to talk about today. We're going to talk about some of the different types of computer design parameters, and I'll explain what that means. We're going to review geometric constraints, which we talked about way back in Unit 4 when we first got into Inventor. Parametric constraints is the real topic of today, and we'll look at how we can use parametric equations to maintain the proportions of a model even if we decide to change its size around a little bit. The word parameter means a property of a system whose value determines how the system will behave. So when we put things like dimensions on a CAD model, those dimensions are parameters that are telling the model how to behave, what size and shape it should be. And there's all kinds of ways that we can handle those parameters in a CAD model and change them around to behave differently. 3D CAD programs typically have three different types of user-defined parameters, and they are geometric constraints, which we've talked about before. We'll review that a little bit. Assembly constraints, which should also look familiar, and I'll review those real quickly, and parametric constraints, which, believe it or not, we have used a little already, but not to the extent that we're going to learn about them today. Geometric constraints are non-numerical relationships that the user assigns to sketched elements. So, for example, every time you use a constraint to make two lines parallel to one another, that is a geometric constraint. You didn't have to type in any numbers. There's no numerical values to it, but you're just making those two lines behave in a certain way, making them parallel, or making two arcs concentric, or making a line horizontal. Each of those is an example of a geometric relationship, not a numerical one. So we should be somewhat familiar with these little icons in Inventor. These are the 12 geometric constraints that you can apply in a two-dimensional sketch. Coincident, collinear, concentric. You can fix the geometry. You can make it parallel, perpendicular, horizontal, vertical, tangent, smooth, symmetric, or equal. Assembly constraints are a little bit different. These are also non-numerical geometric relationships that the user assigns to the parts of an assembly, and these limit the parts' degrees of freedom. We've talked about degrees of freedom when we've talked about assemblies. Every direction that an object can move is referred to as degree of freedom, and there's 3 or really 6 degrees of freedom in three-dimensional space. Something can move up or down, front to back, and left to right. If you lock one of those down in a way that it can slide, it may be able to rotate still. So there's different ways to think about the motion of parts in 3D space. But in general, an assembly constraint is going to limit one or more of those degrees of freedom. So for example, mating the surface of a part to another surface, that's going to lock down 1 degree of freedom. Inserting a peg into a hole is going to lock down at least 1 degree of freedom. Making a round part tangent to a flat part, that's going to lock down 1 degree of freedom and limit the direction that those parts can move in. When you use assembly constraints in Inventor, this is the window that you see, and 99% of the time we tend to use the same 2 constraints, mate or flush, to deal with flat surfaces, but there are a lot of other assembly constraints in there that you can use for when the situation calls for it, like establishing a specific angle between 2 surfaces, making a round surface tangent to a flat one, inserting something into something else, or making 2 parts symmetric. Parametric constraints are something a little bit different. They are used to control the size and location of geometry. So your standard sketch dimensions that you put onto a 2D sketch are parametric constraints. We've been doing that since the beginning. If you type in a specific numerical value, such as 2 inches or 25 degrees for an angle, That's a parametric constraint using numbers to control the geometry of the sketch. But those parametric constraints can become a little bit more complex. They may take the form of abstract algebraic formulas, such as what you see on your screen here, d2 times d0 divided by d5. What you see there, those d2, d0 numbers, are designations given to dimensions. Every time you add a dimension to a model, it gets a designation like this one, starting with D0. The first dimension you put on a sketch would be designated as D0, regardless of what you type in there. You could type in 1.5 inches, you could type in 45 feet, whatever the value of the dimension is. It doesn't really matter, but D0 would be the designation for that dimension. Later on, if you wanted a different feature of the part to have a physical relationship to that original dimension, D0, you can use D0 in the dimension of that later feature. So I'll explain what I mean here. Sometimes for certain models, it doesn't make a lot of sense to create the model and all of its dimensions individually, one at a time, every time you reimagine the part in a different way. So an example might be somebody who designs shoes. Shoes come in lots of different sizes. And if you make a great design for a pair of shoes, you don't want to have to then create a brand new model and redo all of the parts and pieces of that shoe just to get a size 6, a size 7, a size 8. You want to be able to make one small change somewhere in the model and have all the rest of the geometry automatically update, because it's not defined by numbers, it's defined by relationships and ratios. A good example would be a set of gears. For a set of gears to work together, they have to have a tooth pattern that matches. And that tooth pattern needs to remain the same regardless of how big or how small the gear is. So if we have a smaller gear driving a bigger gear, those gears are going to have the exact same tooth pattern. They're just going to have a different sized wheel in the middle that those gear teeth are attached to. So the dimensions that govern the shape of those gear teeth might be created using parametric equations. And if this gets to be very complicated, as it can be with gear teeth, we can actually tie those complex values and formulas to a spreadsheet. We've spent some time working in Excel spreadsheets. That's a great way to define complex parameters for parametric modeling. And you can figure out all of the parameters for something complex like a gear, and then you can use the parameters you define in that spreadsheet in conjunction with the CAD program, and you can get the spreadsheet to tell the model how to be. If you do this right, you can make one small change, like to say change the diameter of the gear, and you can change that aspect of the part without interfering with the size or shape of the teeth, because the teeth need to remain the same size and shape in order to work together with the teeth of a larger or a smaller gear. Parametric equations are algebraic equations that use variables which can be substituted for individual numeric values. So I already mentioned that each time a dimension is created, it gets a designation, such as D0, D1, D2, and so on. Sometimes, for certain models, you want to create a relationship that's more important than the actual numerical value of the dimension. So instead of typing in a specific number, if you want that number to be flexible for making different changes in your model, you'd use algebraic equations to do this instead. So in this example, whatever the relationship of D7 is, it's more important that it have the correct relationship to the existing dimensions D2, D0, and D5. So instead of typing in a number for D7, the user might have the relationship figured out and expressed in this equation: D2 times D0 divided by D5 plus 2 inches. Then, no matter what the value of D2, D0, or D5 is, it will automatically adjust the value of D7. And if a change is made to D2, D0, or D5, D7 will update automatically. To type these parameters, we need to obey the order of operations very closely. We have to type these equations out as though we're typing them into a calculator, which means if we want an operation to happen first, we have to put parentheses around it. Otherwise, it is subject to standard order of operations, and it's going to do things like multiplication and division before it does things like addition and subtraction. If you wanted the addition or subtraction to happen first, you'd need to put those things in parentheses so that they are what the program registers first. Another good example of where parametric equations might come in handy. A child's proportions are similar to those of an adult, but they're just smaller. So if you were designing a chair for a child and you already have an existing chair model for an adult, you could resize and reproportion the entire child's chair with just one quick update to your CAD model if it was designed with parametric equations in the first place. Then you wouldn't have to go along and re-enter new values for each and every dimension of the model. You'd be able to adjust one dimension, like for instance the height of the seat off the ground, and all of the related dimensions that follow would automatically update. You'd end up with a proportionally appropriate chair. And you could choose not to include certain things like, for example, the thickness of the wood. You're probably going to be working with the same thickness of wood on the adult chair as you are on the child's chair. So that dimension in the original model would not be created using parametric equations and a relationship. Those would just be absolute values of the thickness of the wood. So as I've said, as you're creating a model, each dimension is given a designation, starting with D0. So what we're seeing in this model is the value of the different dimensions, what their actual magnitude is. Here, those magnitudes have been replaced with the designations of the dimensions. So D0 would be the depth of the part, the first dimension that was placed on the first sketch. D1 being the width of that rectangle that was also applied on the first sketch. Then, when the rectangle was extruded, it got two new dimensions, D2, which is the thickness of the part, and D3, which is the taper angle of that extrusion. We usually use 0 for this, but we've also seen how we can use a taper angle in an extrusion. Every time you make an extrusion, it gets a taper angle with a dimension designation, whether or not you put an angle on it. All of the location and size dimensions are given designations. Geometric constraints, like if you made something perpendicular or parallel, do not have designations of D0, D1, and so on. As I said, extrusions and taper angles are also given designations. Even if you don't type something special in for a taper angle, it's still there, in this case as D3, with a value of 0. In this example, for the plate that we're modeling, the plate might be manufactured at different sizes, but it's important that the ratio of the overall plate depth to the overall plate width remains constant no matter what size the plate is manufactured to. So if the plate were scaled up or down, the overall dimensions would remain proportional to each other. If the overall plate depth and overall plate width must maintain a constant ratio, then the current dimensional values can be used to establish the ratio. In this case, the plate is starting out with a depth of 3 inches and a width of 5 inches. Instead of typing in 5 inches for the width value, we'd like to be able to type in a parametric equation that will preserve that relationship in size, even if the plate depth is changed from 3 inches to something else. We want it to have the same relationship or maintain the same proportions. So that proportion is, in this case, a 5:3 ratio. So we can use the ratio 5/3, or if we express this fraction as a decimal, we could use 1.66 repeating. But in this case, because we have a repeating decimal, I think it would be a little smarter to use the fraction in our parametric equation. If we wanted to reverse this around, we'll see another way that we can type this as 3/5, which does have a nice tidy decimal of 0.6. That could be used instead. So there's two different ways we could type in this parametric equation to preserve the relationship in size between D0 and D1. For D1, we could either type in D0 times 5/3, or we could type in D0 divided by 3/5. Mathematically, these are equivalent equations. They are both going to give us the same result. If D0 equals 3, it's going to produce a D1 that equals 5. If D0 equals 6, it's going to produce a D1 that equals 10. It's going to preserve that relationship of size no matter what we type in for D0's value. So there are oftentimes multiple different correct ways that you could express the parametric equation for a given dimension. This is just an example of that. Each parametric equation must tie back directly or indirectly to a dimension that has a true value. In this case, the dimension D0 has a true value of 3 inches. Dimension parameters are named in sequential order beginning with D0. The first dimension you place will be labeled D0, the next D1, and so on. In the process of creating a model, if you decide to delete a sketch that had a few different dimensions on it, the designations that went with those dimensions go with them. So from there, any later dimensions that you added will still have their same dimension designations, and you would essentially just lose a few dimensions from the middle of your model if you delete those dimensions. So in this case, if I deleted D1 from the sketch and then placed the exact same dimension right where it was, its designation would be D2, and I just wouldn't have a D1. So I'd have to be careful not to use D1 in any of my parametric equations moving forward, because the computer's not going to understand it. There is no D1, it's D2 now. You have to keep your designations neatly organized in order for this to work. So when you're doing this in Inventor, you can type in equations into the dimension dialog box instead of a number. We're used to typing in a specific number for the dimension of a part, but we can type in parametric equations, and we can use the D designations for existing dimensions, like D0 times 3/5. When you're looking at sketches in Inventor, you can change the display mode of dimensions by right-clicking and choosing Name as the dimension display in order to display the parameters instead of the numeric value. As you create dimensions and parameters, they're actually being recorded in a table called the parameter table. And this displays the parameter names, the units, any equations that you used, and the numeric values of those dimensions. If you click the Manage tab in Inventor, that's where you can find the parameter table, and it keeps like a running log going of all of the dimensions that you have in your model, what their designations are, and what their actual values are based on the inputs that you've given. You can make changes in the parameter table, which is a convenient way to update and change things. So if instead of using D1 for the width of the part, you wanted to just write width instead of D1, you could do that. But then every time that you reference the width of the part for the rest of the entire model, you have to remember that that dimension's name is width, not D1. So you'd have to type width into your equation in place of the designation D1. On the right-hand side, you can add little comments to help yourself remember what the different dimensions are in your model. Next week, we're going to do a little bit of practice with parametric equations. And without having Inventor at home, I'm going to do my best to sort of simulate how we can construct these parameters and these equations with the correct relationships. You won't need to have Inventor to do this. I will be sharing information with you about that next week when I post the assignments. For today, you just need to be clear about how parametric equations work, what their purpose is, and how they're different from the other types of parameters that we've used along the way throughout the year, the geometric constraints and the assembly constraints. And that way, when you see the assignment and we work on completing one of these parameter tables on our own, it won't seem terribly unfamiliar. If anything about today's lesson was unclear, if you need to ask questions or get some clarity, feel free to reach out to me. I'm happy to answer your emails, and I can talk to you during office hours if you prefer. Good luck.